Hello everyone. Today we are going to talk about one of the most important questions in antiquity. That was how to define area of some region, or how to actually calculate area of some region. Now we know how to calculate areas of, say, rectangles or triangles or even polygons, but this question becomes very complicated once we move into something like circles, right? Or the same question as how can we figure out volumes of a sphere. Now all these questions are related to something which we now call integration, but the first time actually we have seen integration is long before Newton or Leibniz. That is in the 3rd century before Christ. A great mathematician of all time, Archimedes, he actually figured out a way to find the area of a circle. Okay, so that idea is at the heart of what we now call integration, and we're going to show today what problems we face when you want to figure out areas of regions which are not as nice as polygons, and then we'll see what Archimedes did, and then in the next videos we're going to actually extract those principles to find areas of more general region. Okay, so let's start with this circle problem. So today we are going to see area of a circle, but let's start with this problem, area problem. Okay, so let me ask you a few questions. Suppose we have a rectangle of say length L and width W. Now what is the area of this rectangle? Area of this is just length times width, right? It's that simple. And the second one is, what is the area of a triangle that has length L and height H? Yeah, we know that this area is 1/2 times length times height, right? And then the third region is this, something like a polygon. So like this. And if you want to figure out area of this kind of region, then the idea is this: we will draw some chords. Okay, so let's say this one, and that one, and one more. Okay, then it splits this polygon into few rectangles. So this is, let's say A1 is the area of the first rectangle, A2 is the area of the second one, A3 is the area of the third one, A4 is the area of the fourth one, right? And then area of this is just the summation of those four summations of the areas of those four triangles. Okay. So it doesn't matter how many sides we have, we can always find area of a polygon. We can just split this into triangles. Now that was very nice and clean, but then we have this kind of situations that we cannot avoid. So circle is kind of a divine geometric structure in the Greek mythology and in other mythologies in the world. We think about circle, you know, like it's kind of completion of life and death. You start at one point and then you finish that, and then it keeps going and going. So it has a lot of importance from different perspective. But the question is this: suppose we have a circle of, say, radius r. Okay. Now what is the area of the circle? Right? It's hard to calculate. So how can we calculate this thing? So one way of calculating this is to approximate the area by polygons, right? And that's the right idea, but the problem here is this. Suppose we draw a circle of radius r, right? And then suppose we draw some inscribed polygon. Okay, I cannot finish this. But still, you'll see there will be some regions outside of that polygon, right? So I can calculate area of this polygon using this formula, but still it's not giving me the actual area of the circle. Then how can we actually finish this process? Okay, so Archimedes thought about something really amazing. What he thought is, suppose we have this polygon there. If we keep increasing the number of sides, let's say we are increasing one more side, one more vertex there, so that will increase two more sides, and then another one, another one, another one. Oh God. Finally that. Okay. Then this blue polygon actually captures more area than the previous one, right? And then if you keep doing and doing and doing, then what happens? At some point this will fill up as many space as you want, right? Now you may notice already what Archimedes was thinking is to take some kind of limit, okay? And to calculate the area of a circle, there is no other way than taking a limit. And that was actually the first instance where people used limit to find some concrete things like area of a circle, okay? Now, I'm not going to show you the proof of Archimedes. Actually, I have never read that proof, but there is a variation of that proof that I know, and I'm going to show you how can we calculate area of a circle of radius r. We all know this area. We know this area is what? This area A is pi r square, right? And there are different ways people actually calculate this area. Some of those techniques give exact formula, but those techniques are not correct. And then there is integration technique. You can actually write down the equation of this circle and then use strict substitution to calculate that area. But that's not what I'm going to do today. I'm going to show you how to calculate area of a circle from a very, very primitive technique. Okay, so that will be the end of this video, and after that we'll talk about Riemann integration in the next videos. Okay, so where should I start from? Okay, so let's just start from here. Okay, so this is example. Show that the area of a circle of radius r is pi times r square. Okay, now how we'll do this thing? We'll do this thing in two steps. Okay, so let Pn be a regular polygon of n sides. Okay. Regular polygon means it's a polygon whose all the sides have same length. Okay, polygon whose all the sides have same length is called a regular polygon, and it has n sides. Okay. Oh, sorry, I need to say something else. Let Pn be a regular polygon of n sides inscribed in a circle of radius r. Okay. I have to draw the same circle here one more time. I wish this becomes a circle. Okay, close to that. drawing a circle is a really, really hard thing. Okay, so this is the center. Let's say this much is my radius. Okay, and I want to have all the sides of this polygon to be equal, and also all the vertices should be on the perimeter of this circle. Okay, so let's say this, 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 so this. Okay, let's say these are the vertices, and then we'll join those. Okay, so this is my PN. Now, we need to calculate area of this PN. Okay, now the question is this: what is the area of P sub n? That's not too hard to compute. Notice all this, so from the center I will join the vertices like this, like this. Okay, now, yeah, clearly this is much narrower than this one, so anyway, also, yeah, this should be much narrower, but yeah, we are not drawing this accurately. Anyway, so all these triangles will be congruent, okay, because these sides are actually equal to the radius, and these sides are same, so they have the same sides, and then they will be congruent, right? So what happens, all these angles are same. Actually, this angle is the same as this one, is the same as that one, is the same as that one, all of them, right? But how many of these angles are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is a 9 gone, so there will be 9 angles, right? So in total, it will have n of those angles, right? So what we're going to do is this: we'll take just one triangle like this. Okay, so let's call this triangle O. Let's say this one is A and B. Okay, all right, so joining the vertices of the polygon with the center of the circle, we get, what do you get? N congruent triangles. Right? And therefore, each of these triangles have same area. Okay? So now if I can figure out area of, say, this triangle and then multiply this by n, then I will get the area of this whole polygon. Right? Okay? So let O, A, B be one of these triangles. Okay. Then the area of Pn is this, n times the area of this triangle OAB. Okay. Now, what is the area of this triangle OAB? That's half times base times height, right? And notice base has length, the radius of the circle, it's r, right? Now, the area of the triangle OAB is what? Half times base times height, okay, which is equals to half times r times let's say h, where h is the height of this triangle. Okay, and we know what r is, we know what 1/2 is, so what we need to do is we need to figure out what h is. So let's draw a perpendicular line here. Okay, so let's say this much is h. Then can you see a relation between this h and r? Notice this is a perpendicular, right? So this becomes a right triangle, right? So let's say this angle is theta, okay? Then h is the opposite and this much is the adjacent, right? So opposite over adjacent is tan theta, right? But the problem is we don't know what this quantity is, so we cannot actually use that. But notice this much is also radius, right? And opposite over hypotenuse is sine theta, so we can use that relation, okay? So let this angle OAB equals to theta, okay? Then h over r, which is opposite over hypotenuse, is sine theta, right? That means h equals to r sine theta. Okay? By the way, how much is theta? What is theta? Notice this is theta, so that is theta, so that is theta. All of them are theta, right? And there are n of this angle. So n times theta is this 360 degree, right? So it is 2 pi. Notice n times theta is 2 pi, and that gives theta equals to 2 pi over n, right? So therefore height is r times sine 2 pi over n, okay? And that means area of OAB is what? 1/2 times r times that. Therefore the area of this triangle OAB is 1/2 times r times h is r sine theta, and theta is 2 pi over n, which means this area is 1/2 times r square sine 2 pi over n. Okay, so that's the area of just this piece, this triangle. And there are n such triangles. They are all congruent, right? Therefore, the area of this polygon is n times this. Okay? And hence, the area of PN is what? N times 1/2 r square sine 2 pi over n, okay, which is 1/2 r square times n sine 2 pi over n. Okay, so now we know the area of any regular polygon of n equal sides which is inscribed in the circle. And then what Archimedes said? Increase the number of sides, right? So increase n. N is the number of sides. So if now I have what? So 9 sides, right? So what I need to do, I have to increase this thing, right? So then this, let's say I double this thing. So this will be 18. It's really hard to draw now. Okay, and then keep doing and doing and doing. So what's happening actually? The number of sides of the polygons, which is n, that number is going towards infinity. Okay, so that's the technique. So therefore the area of this circle is limit n tends to infinity of this guy. Okay, therefore actually I need to be a little bit precise here. Okay, so area of this polygon is definitely less than area of the circle. Okay, so I actually go very rigorous on this now. Area of Pn is less or equal to area of the circle of radius r. Okay, and area of Pn is what? 1/2 r square times n sine 2 pi over n. This guy is less or equal to area of the circle. Okay. Circle of radius r, right? And notice no matter how many sides your polygon has, it's still inscribed in this circle, right? So if n goes to infinity, even though that area will be less than the area, less than or equal to the area of the circle. Okay, so since this function is less or equal to that, so by the limit property we can get therefore limit n limit of 1/2 r square n sine 2 pi over n as n approaches infinity. This guy is less or equal to area of the circle of radius r. Okay, so that's one thing we have got. Can we figure out this limit? Yes, we can. Okay, and let's figure out this limit. Okay, so here's the thing. Notice limit of 1/2 r square n times sine 2 pi over n as n approaches infinity. That limit is what? 1/2 r square. Since this limit is on n, so 1/2 r squared, that's constant, we can factor that out, right? So this is limit of n times sine 2 pi over n as n approaches infinity, right? Now, does this look familiar? Maybe not now, right? But if I just write this n in a different way, you will see this is familiar to something that you have seen many, many times. So this is, notice I can write this thing as sine 2 pi over n over 1 over n. Right? because 1 over 1 over n is just n. Okay? Alright, we need just one more thing. What is it? If we can have a 2 pi over here, then actually we can use the fundamental limit, right? Okay, so the next thing we're going to do is we will multiply 2 pi on top and bottom. So this guy is now 1/2 r squared times, I will multiply here 2 pi, limit n goes to infinity, sine 2 pi over n over 2 pi over n. Right? So it's the same thing. We can cancel out 2 pi from top and bottom. Okay. Now what I'm going to do, I'm going to change the variable. Actually this is, notice 1/2 and 2, they will be cancelled. So this is just pi r square times limit. So what should I do here? Okay, so let's call this guy u equals to 2 pi over n. Okay, so then this is sine u over u. Okay, and as n goes to infinity, where does u go? U goes to 0 from the right. Okay, so this is the limit of sine u over u as u approaches 0 from the right. But that limit is 1. That's a very important limit. We call it the fundamental limit, right? So that limit is, okay, so I should write here, this guy equals to this, where u equals to 2 pi over n. Okay, so now this limit is just 1, so this is pi r square. Okay, so what we got? We got that the limit of those regular inscribed polygons is pi r square, and that limit is less or equal to area of the circle. Okay, we had some inequality written here, so we get this. Thus pi r square is less or equal to area of the circle of radius r. Okay, we got one inequality, but that doesn't quite say that area of this circle is pi r square, right? It can be slightly bigger than pi r square. Okay, so we are not quite done. We need to do something else. We need to show that area of the circle of radius r is actually less or equal to pi r square. Okay, then it cannot be bigger than pi r square, so it has to stick to with pi r square, and there you go. Okay, so how can we do that? Notice these are inscribed polygons, and they are, you know, inside this circle, so they cannot actually make areas bigger than the circle, right? So what else can we do? Or what else actually Archimedes thought? Archimedes thought a really nice thing. He thought, okay, now at this moment, instead of taking inscribed polygons, let's take circumscribed polygons. Okay, and that will actually give you the other inequality, and then you'll be done. All right, so now let's just okay, I have to erase this picture now anyway. Okay, so now let Qn be a regular polygon of n equal sides. I mean, regular means equal, so we don't need to say that, of n sides circumscribed in a circle of radius r. Okay, so this time oh God. Does it look like a circle? Kind of. Okay. Kind of is good. So let's say this radius is r. Now instead of taking inscribed polygons, we will take circumscribed polygons. So they will have sides which are tangent to this circle. Okay, so let's take this to be our first. And all the sides have to be of same length. That's why it is regular. Okay, and then okay, get this. Oh God. Okay, you just have to believe that this is a regular. It doesn't look regular at all, but okay. Yeah, this picture has nothing to do with the proof. Yeah, it's just to give you the idea of what we are doing. Okay, so this is a regular polygon of n equal sides circumscribed in the circle. And just like the previous case, notice if we join these chords, let's say, yeah, this, then we get n congruent triangles, right? If we join the vertices with the center, of the circle, we get n congruent triangles. Okay. And what will happen then is the area of this circumscribed polygon Q sub n will have area that is n times the area of any of these triangles. Okay, so let's take this triangle. Let's call this OAB. Okay, so let OAB be one of these triangles. Okay, then the area of Qn is n times the area of this triangle OAB, right? So just like the previous case, now we have to figure out area of this one triangle. And once we can figure that out, we can multiply that by n, and then we can take the limit, and then we'll be done. Okay? All right, so what can be the area of this triangle? Notice this, at this point, this is, this polygon is tangent to this circle. So this radius is actually r. Okay, let me draw this triangle very well. All right. Now what will happen, you know, since this is a regular polygon, these angles will be the same. Okay. And these two triangles will actually be congruent. So what will happen, that this line will be a bisector of this angle. Okay, so this much will be exactly equal to that. All right. Now what is this total angle? So let's just draw this guy in yellow. Okay. What is this angle? AOB. Notice this angle AOB once again, since this is a regular polygon, okay, all these triangles will be congruent, and so these angles will be the same, and n of these angles will make 2 pi, right? So notice n times this angle AOB is 2 pi, and therefore angle AOB equals to 2 pi over n, right? Okay. Then let's say this point is C. Now since this is a perpendicular bisector, this angle will be exactly half of that. Okay. All right, so let C be the point of contact of the side AB and the circle. Okay. Then OC is perpendicular to AB, and hence this angle AOC is going to be half of the angle AOB. Does it make sense? So this is AOB, AOC, and AOB is the yellow one. Okay, so this is half of the angle AOB. But what is angle AOB? That is 2 pi over n. So this is 1/2 times 2 pi over n, and you can cancel out 2 from top and bottom, so this is pi over n. Okay, so now this angle, the blue one, is pi over n. Okay. Actually, what are we doing here? We are figuring out area of this triangle AOB, which is half times AB times the height, which is r. We know what r is, so we don't need to worry about that. All we need to worry about this AB, right? And notice, since this OC is a perpendicular bisector, so all we need to know what AC is. Then AB is just 2 times that. Okay? So we need to figure out what AC is. So how can we do that? How can we do that? Just like the previous case, you know, there will be some trigonometric functions to rescue. So we need what AC is. Okay, we know what this guy is. Can you find a relation between those two? Of course, this is my angle, so this is opposite and this is adjacent, right? So opposite over adjacent is tangent, right? Tan. So AC over R is going to be pi over n. Okay, there you go. All right. Now AC over OC, which is R, is tan of pi over n, right? So that makes AC equals to R times tan pi over n. And since OC is a perpendicular bisector, AB is 2 times AC, so that makes it 2R tan pi over n. Okay, so we know what AB is, we know what OC is, and then we can actually get area of this triangle OAB, right? Hence, the area of this triangle AOB is what? 1/2 times base, which is AB, times height, which is OC. Okay, so this is 1/2 times 2R tan pi over n times OC is just R, so you can cancel those two out, so this is R square tan pi over n. Okay, so that's the area of one of the n triangles, and therefore the area of this circumscribed polygon is n times this. Okay, and therefore the area of Qn is n times R square tan pi over n. Okay, so what I'm going to do, I'm going to factor out R square and then R square times n tan pi over n. Okay, now notice as you increase the number of sides, which is n, okay, then these guys will become smaller and smaller. So it's kind of like this thing we did earlier. Now this will look like this. So length of the sides will be decreased, but number of sides will increase. So that's the technique. Okay, so now look at this blue polygon. It has more sides, number of sides have increased, right? And then notice it is much closer to the area of the circle. Still it's bigger than the area of the circle, right? Okay, so just like the previous case, what we have to do now, we also need to take limit as n goes to infinity. Okay, so we are gradually shrinking down this thing. Okay, so now notice all these polygons are circumscribed, right? So definitely they will have some areas, some regions which are not covered by the circle. So that definitely that will have much bigger area than the circle. Okay, so notice the area of the circle of radius r is less or equal area of Qn for all n, right? No matter how large the number of sides of this polygon is, still it's circumscribed, right? And therefore has bigger area, or at least equal to this area of the circle. Okay, and that means area of the circle, now we are taking limit on both sides. Okay, now notice this area of the circle, it does not depend on n. The area of the polygon depends on n, right? So if I take limit n goes to infinity, on this side it remains the same. So area of the circle of radius r, or this guy is less or equal to limit of what is it, r square times n times tan pi over n as n approaches infinity. Does it make sense? It's the same process, just coming from the other side, right? Okay, so this limit is on n, so we can just factor out r squared. So this is r squared times limit of, notice this guy tan, which is sine over cosine, right? Okay, so we can just write this guy as sine pi over n, okay, over cosine pi over n, right? And this n, just like the previous case, we can just write this as 1 over n, right? So this is 1 over n, okay? And you can actually sense where we are going. We want to use the fundamental limit, right? For that reason, we need to have the same amount inside sine and at the bottom, right? So we need a pi over there. So we have pi r squared. I'm multiplying top and bottom by pi. Limit n approaches infinity, sine pi over n over pi over n times 1 over cosine pi over n. Okay? One thing is pretty obvious. As n goes to infinity, pi over n goes to 0, and cosine is a continuous function, so that limit is cosine of 0, which is 1, so that's a really nice thing. So then this guy is pi r square, limit n approaches infinity. We're going to distribute this limit, actually, use the product rule, pi over n, okay, and then the limit of 1 over cosine pi over n. Okay. Then that means area of the circle of radius r is less or equal to what? Pi r squared. Then we have this limit here, sine of something, that is 1. Okay, I'm telling you again, as n goes to infinity, pi over n goes to 0 from the right, but cosine is a continuous function, so that limit is just cosine evaluated at the limit of pi over n, which is 0. So cosine 0, which is 1. Okay, so this is 1 over 1, which is 1. Now here, what we need to apply the fundamental limit, we need to change the variable, right? So we'll call pi over n as my u, where u equals to pi over n, just like the previous case. Okay, so this is sine u over u, but as n goes to infinity, pi over n, which is u, goes to 0 from the right. Okay, and that means this is what? Pi r square. This limit is 1 times 1, which is pi r squared. Okay, so we're done. Now, in the previous case, when we took inscribed polygons, we saw that area of a circle of radius r is bigger or equal to pi r squared. And then when we took circumscribed polygons, then we saw area of circle of radius r is less or equal to pi r squared, right? So if we combine those two, what do we get? That area of my circle of radius r is between pi r squared and pi r squared. That means it's definitely equals to pi r squared, right? Okay, so that's what I'm going to do now. Therefore, now pi r squared is less or equal to area of the circle of radius r, and that is less or equal to pi r squared, i.e. area of a circle of radius r is pi r square. Okay, so we all know about this formula, but how many people know why this is true? Okay, just imagine this thing like how many 2,300 years ago you figured out this thing. How excited you'll be. Yeah, Archimedes was similar kind of excited. And that's why he had this eureka moment, those eureka moments, right? Anyway, so what was the point of doing this thing? First of all, this is a really remarkable approach to solve a problem. Okay, people didn't know what to do with area of this kind of regions. Archimedes showed them how to solve these things. And this is at the heart of what we call integration. Okay, sorry for this long route, but what is the essence of this thing? We did chop the region into several pieces by some kind of geometric objects whose areas we can calculate. And that is what is going to happen with functions in general. Okay, we are going to define what a Riemann sum is, and the idea of forming that Riemann sum is exactly like this. So I'm going to end this video asking that general question, more general question. Suppose we have a function, how are we going to define its area, and moreover, how can we calculate that area? Okay, so I'm going to pause that question and I'm going to give you a brief hint. So from Archimedes, what we can actually learn, and then I'll end this video. Okay, so here's the question. So I guess I asked four questions earlier. I answered all of them. So now this question 5. Okay, so question 5. Oh, let's not number this thing. Okay. Let f be a function defined on a closed bounded interval. We need bounded interval for this on a b such that, okay, we need one more thing, or we can actually relax that restriction, but for now just to motivate the thing, such that this function is positive. Okay, f of x is positive or 0 for all x in a b. Okay, and the question is this: what is the area of the region bounded by the graph of f, the x-axis and the vertical lines. X equals to A and x equals to B. Okay, so in other words, we mean this thing. We have a function like this. Okay, and this is x-axis, this is the graph of my function, and this is the vertical line x equals to A, this is the vertical line x equals to B, and this region. How are we going to figure out this area? Isn't it crazy? But we can actually, just following Archimedes. Okay, so the lesson we should learn from Archimedes is, if you have a region like this, you need to piece it into small pieces and then fit something that you can calculate, such as, what kind of things we can calculate actually? Triangles, but what is better than triangle? Rectangles, right? So the idea here is this: we need few ideas. The ideas to solve these problems are this: partition. Okay, so that's what Archimedes did. He took this whole circle and then what? He put a polygon inside that, right? And then all those polygons actually give you triangles, those areas you can calculate, right? So you, it's not accurate, but at least you're going to start with few pieces that you can handle. Okay, so partition. So what does partition mean? Partition means this thing. So this point, we'll call this x sub 0. Okay, that's the starting point, and this point we call this x sub n. Okay. N is the number of sub-intervals. So this is an interval, and you are going to subdivide this interval into n sub-intervals. Now this n, okay, so when you want to calculate the exact area, this n has to be very large, because you need to make this very, very precise, right? But then when you want to calculate, when you want to approximate this area using some numerical methods, then you can actually choose a specific value for your n, say 10,000 or 20,000 or much bigger than that, okay? But when you are talking about integration, then this n is a variable. We need to keep this n growing and growing. Ultimately to go towards infinity, that's the goal. Okay, so in between we are going to take few points. Okay, let's say this one is x sub 1. Okay, this one is x sub 2. Let's say this one is x sub 3. Okay, and let's say this partition has just 4 points. Okay, so I have subdivided this original interval into 4 subintervals. Okay, so that's partition. Okay, and then what you need to do, you can think about partition in Archimedes cases. You know, like for the inscribed polygons, you can think about those polygons that are inscribed in the circle, right? And their vertices, you know, those vertices are equally spaced. They divided the arc, I mean the perimeter of this circle into pieces, right? That's the partition. Okay, now from each of these partition, we need to do something. Okay, so Archimedes had triangles, right? We don't need triangles. We can actually do much better than that. What can we do? We can actually fit some rectangles. So that's the next idea, fitting rectangles. Okay. So how do you fit the rectangle? So one thing is, once you choose this partition, you know, this is going to be the width of your rectangle. So that's fixed. But how much will be the length? That depends. Okay, and then you have a freedom. So what you can do, you can take any point from this subinterval, anything. Okay, so for this one, let's say I will take this one and I will call this, let's say, t sub 1. Okay, t sub 1, and we will evaluate this function f at this point. So this is f of t sub 1, right? This height. Okay, so I will take that as the height of my rectangle. Okay, so then what kind of rectangle do I get? I get this one. Okay, so once again, notice how, what is the height of this rectangle? This is f of t sub 1, right? And what is the this is what is the length of this? This is x1 minus x sub 0. Okay, we'll call this delta x sub 1. Okay, so that's the width, this is the length, and then when you multiply those two, you get area of this rectangle. But notice here you have some, gains. You have some extra areas that was not actually bounded by this graph and the x-axis, right? And notice here are some losses. Okay, there are actually some areas you could not figure that out. You could not actually capture those areas by that triangle. Okay, but it's okay. It's okay. So now for this interval, okay, let's take some points. So let's say, see, these points can be any points. It doesn't have to be the midpoint. It doesn't have to be the leftmost point or rightmost point. Although there are like many different places, there are advantages of taking just the right points. There are advantages of taking just the left points. There are advantages of taking just the midpoints. And there are actually some other cases. I mean, none of them will work. Okay, so this is very flexible, but that's very important. That's the power of Riemann integration. Okay, so let's for this one, let's say I will just take this guy. Okay, so this guy is my T2. Okay, I can take this one, and then I will fit a rectangle there of this height. Okay, so this one. Okay, now this rectangle has what is the height? This has height f of t is 2. And what is the length? Length is we will call this delta x2, which is basically x2 minus x1. Okay, and then you keep doing this thing. So this is fitting rectangle. So you do this for all of these subintervals. So now for now, let's say this is t sub 3, and then you get this rectangle, and then this is, let's say, t sub 4. Okay, so first we made a partition of this interval, then we fit rectangles, right? But this rectangle, notice it has one hidden thing. So what does it mean? It means that first these rectangles will have length, what is the length? F of t sub I, and width delta x sub I. Okay, delta x sub I means xi minus xi, x sub I minus 1. Okay, and what is t sub I? Where t sub I is any representative point of the subinterval x sub I minus 1 to x sub I. Okay, so that's what fitting rectangles mean. And then you need to do what? Form Riemann sum. Okay, so what is Riemann sum? Riemann sum is the sum of these areas of rectangles. Okay, so this is like, what is this? This is summation of f of t sub I, and then delta x sub I goes from 1 up to n. Okay, so that's what a Riemann sum is. It's when we calculated the area of that inscribed polygon or circumscribed polygon, right? So still following Archimedes, right? If you can do something in math, man, okay, that will remain forever. Not always. Okay, but there is a very, very important point at the end that Archimedes did. What is it? You need to actually refine your estimates, right? So that's the last thing. This is called refinement. So what does refinement mean? Here you have some gains and some losses. Here you have a lot of losses. Here it's pretty good. Here you have some gains and losses, right? But then how did Archimedes actually refine that thing? Archimedes took more sides. Okay, so if you increase the number of sides, then the gap between the area of the circle and the polygon decreases, right? So here now what you do, you will actually take more points. Okay, so now let's say this is x sub 0. Okay, let's say this is going to be your x sub 1. Then you take, say this is your x sub 3, oh sorry 2, this is x sub 3, this is x sub 4, this is x sub 5, this is x sub 6, this is x sub 7, and so this is x sub 8. Okay, so you have doubled the partition. So what you did, you have taken more points on this interval, but you have taken more sub-intervals, right? And what happened then, those sub-intervals actually have shrinked down. And now if you want to actually, if you choose points, representative points from each sub-interval, then let's say this one, then the area here is going to be this. Oh god, this joke is killing me. Okay, and for this sub-interval, let's say you choose that, then the corresponding rectangle will have this area, and from here let's say you chose that, then you have this, and from here let's say you chose that, and from here you choose this, from here let's say you choose that. Okay, we are choosing choosing representative points, and then we are evaluating our functions at those points. That gives us height of the rectangles. Okay, and say this one, and say this one. Okay, all right. Now can you see, if you sum the areas of those red triangles, that will give you a better estimate of the actual area, right? This is called refinement. You have refined your estimate. Now, what happened in the case of Archimedes? You took your n to be infinity, right? N is infinity. That means what? Number of sides is infinite. That means the length of those sides are almost zero. Or to consecutive points on the circumference of the circle are so close, right? Very close, 2 points. So that's what going to happen here. You should take let's say this is n, so you should take n to infinity. So all these rectangles will shrink down like really tiny. Okay, and then you will see as n goes to infinity, will this sum approach to some finite number? If it does, then that is called the Riemann integration of the function on this closed bounded interval a to b, okay, which we also call the definite integral of this function. But we are going to talk about those things in next videos. Okay, there will be a lot of setup. We need to actually very carefully write down what partition means, what these fitting rectangles mean, how to form Riemann sum, how to refine those things. But that's the essence. If you understand how Archimedes worked out the circle problem, that's what you need to actually know. And then you will just translate those things in your calculus world and you'll be done. Okay? So that's it for today.